Okay, so a quick announcement before we begin for today. Your homework 9, if you have part 2, you can submit it now or by Wednesday or anytime in my office. That would be fine. This morning I've also posted a short homework 10, which has technically only 2 problems. And the third problem is basically for you to complete the online course evaluation and then submit submit a printout that you've done. So, and maybe if you've already done that, then just go back, log in, and print out a confirmation saying that yes, you have indeed filled that out. All right, so that would be part. So homework 10, which I gave out today, is due still on. Part 1 is due on Saturday. Our final exam would be Monday, 3:30 p.m. downstairs, Hampton, 1252. Let's see, it might be a little cramped there, but hopefully we'll make it work. But part 2 of homework 10, you should submit at least around, well, immediately before the final exam is fine, or earlier in the day in my office is fine too. So, question? Spencer?
What about the equation sheet? We have one, or we have all the.
Right. Yeah. So for final, I think I've allowed in the past 5 letter size sheets. So you can take all the 4 sheets that you had from all the 4 quizzes and add another sheet for this last portion. But I will ask you to staple them all together. I don't want really pages flying all over the place. But yeah, I'll send out an announcement for the final exam as well. Okay. Any questions, Vidhi?
How is it going to be, like, majority of the last portion, like 5th and 6th time?
So I'll post a sample final exam also. But I think there's usually 5 questions, out of which maybe 2 or 3 are focused on this last portion, and 2 or 3 might be on anything before that we have covered in the class. So it would be indeed cumulative. Okay. All right. So very quickly, what I'll do is sort of remind you where we are, and basically, I think the topics that are left to cover are sort of a quick introduction to what a one-dimensional finite element approximation might look like. So before I do that, so this is a quick summary of where we are really. So we know that we have these 3 different forms: the strong form, weak form, and the energy form. If we have the strong form, how do we go to the principle of virtual weak form? Yeah, integration by parts and method of weighted residues, right? So from the strong form, we first write the method of weighted residuals. Then we do the integration by parts to come to the weak form, all right? And if we have the energy form, on the other hand, how do we get to the same weak form? That's minimization. So we minimize where we say d pi u in the direction of the virtual displacement is 0, and that gives me to the same principle of virtual work form of the weak form. From here, let's say if I started with the energy form, once I get to the principle of virtual work form, how do I go to the strong form? Reverse integration by parts and the fundamental theorem of calculus of variation. So indeed, we would do reverse integration by parts, which means unbalancing the derivatives, take all the derivatives from the virtual displacement over to the real displacement, and then you'd have something that would look like a virtual displacement multiplied by a bunch of stuff. And if that is going to be 0, then you apply the fundamental theorem of calculus of variations to get what is called the Euler equation corresponding to the energy form. And the last step is, how do I get from a weak form to the energy form? Now we have to check the Weinberg theorem. If the Weinberg theorem conditions are satisfied, then you can find the weak form. If they are not satisfied, then the energy form does not exist. Okay? Question? Yeah.
Do we always have to check for both the Weinberg?
Yes, absolutely. Both the Weinberg theorems have to be checked and only if both the conditions are satisfied, only then you can conclude that pi functional exists. Okay. Um, and as I pointed out last time, for the Ritz method, what we do is we work with this principle of virtual work form of the weak form, and that's the place where we make our first approximation. In any of these steps, there was no really approximation involved. The only minute difference between all of these three different forms was how regular or how smooth your solution can be. For the strong form, we said that the solution must have second derivatives existing. Otherwise, you can't even write the governing equation Cu double prime plus b equal to 0. For the principle of virtual work form of the weak form, we said the solution must be h1 square, or first derivatives must be square integral. Same thing for the energy form. So there's this only small, very slight difference between the smoothness of these solutions in these three different forms. Otherwise, they are all equivalent. Okay, we have not made any approximation in going between these three states. When we take the principle of virtual work form and we say that now I'm going to make an approximation, we are going to say that I will approximate my real displacement and my virtual displacement with some functions like polynomial functions or trigonometric functions. That's the first place we are making this approximation to come up with what we then called the Galerkin form. Right? The Galerkin form led us to all these systems of equations which look like matrix equations that we normally solve in structural analysis. Right? All right. So keep this big picture in mind always, and what I have here in notes is basically just spelling out what I just said. Another point here, very important to make sure, is that we understand when we are approximating those spaces, what are the conditions on the functions that we can use that we choose to approximate them. So I said that the real displacement will be given by h0 function plus some vector of unknown coefficients times some vector of known functions, right? What conditions does this h0 function have to satisfy? What was the purpose of this h0 function? Yeah, the real displacement must satisfy the essential boundary condition. Anywhere where the real displacement is specified, either it is specified as 0 or 1 inch or 2 inch or whatever, the h0 function must satisfy that given essential boundary condition. And what about the conditions on h? All the other h functions, h1, h2, h3, h4, all of these functions? Say again? Yes, displacement is 0 for all of those functions, or actually those functions are 0 wherever real displacement is specified. So which corresponded to our HEBC, homogeneous essential boundary condition. We said, so I'll write that H0 is equal to U0 on gamma D. Gamma D is the place where displacements are specified. And HEBC says that HI, any of those HI functions, 1, 2, 3, 4, are 0 on gamma D. So the real displacement could be non-zero potentially, but the virtual displacement must be 0 on gamma D. Okay? So keep in mind these conditions, and of course both of them have to be in H1. So there's no, that's something that you're already familiar with. On this next page, I've pretty much redone all of the derivation, so I won't go into too much detail about that. This is just to remind you that how we went between these three different forms. Strong form, you do method of weighted residuals, do integration by parts, cancel out some of the boundary terms to get the principle of virtual work form of the weak form. Remember, we were carrying around that unknown traction at x equal to 0 if where the force or the reaction was unknown. To get rid of that, we introduced this condition, the HEBC, the homogeneous essential boundary condition. And that led us to these two conditions on the real and the virtual displacements. And this is basically what I just mentioned to you, that H0 must satisfy essential boundary condition, all the other H's must satisfy HEBC. If you do that, then you have satisfied all of the conditions on these approximation functions for real displacement and virtual displacement. And then whatever results you might get by doing these numerical method, they can be explained, or you will be able to interpret those results correctly. Okay. All right. And maybe these 2 pages by itself kind of give you a summary of this entire last portion after quiz 4 that we've been talking about. Okay. All right. So let me proceed with what we want to do today. We've been saying that we will approximate real displacement, we will approximate virtual displacement. Till now, we have looked mainly at polynomial functions, right? And you remember those polynomial functions between 0 to L were like linear, quadratic, cubic, 4th order, and so on, so on, so on. Do you see any particular problem with this choice of polynomials? When we are trying to approximate some unknown displacement, unknown real displacement, we want to be able to cover lots of different types of functions, right? Then we will likely get a better approximation. The trouble with this is that as you go higher in order of polynomials, all these functions start to look pretty much the same, right? And what that has a consequence in our numerical computations. The consequence is that what happens is the final system, final matrix K that you get becomes ill-conditioned, poorly conditioned. Anybody know what that means? Poorly conditioned matrix. So you remember well, you all know that matrix have eigenvalues, right? And a condition number of a matrix is defined as the maximum eigenvalue, let me say lambda max, divided by, and actually absolute sign, divided by minimum eigenvalue, lambda min, absolute. So this condition number, essentially what it represents is how well or how easily you can solve that system of equations. You get system of equations K A is equal to F that you want to solve. Now normally what would happen, say for example, if you have a 2 cross 2 system of equations, we know that 2 variables X and Y, for example, represent equations of lines. A well-conditioned system of equations would mean that those lines are very distinct from each other, and you can identify the point where they cross, which is the solution of the problem. You can identify that point or the solution very easily, and a computer would be able to solve that very precisely. On the other hand, an ill-conditioned system, something for which the condition number is very high, means that the 2 equations that you have are very similar to each other. Why? Because all of your approximation functions are very similar to each other. So if the 2 equations that you are trying to solve are very similar to each other, you can imagine that if you do not have enough precision in your equations, then the computer would have trouble finding where do they exactly cross. You have to have very high precision to be able to find where they cross. And that's the trouble with using these types of bases. That if all your functions start to look similar, you will need very, very precise computation to find the solution. Go ahead. Yeah.
So if our solutions are so different, how would you know if you're getting any closer to the exact answer?
What do you mean?
If the approximate solutions that you're finding, and if the functions are very different from each other,
Correct.
how would you know if you're getting any closer to the exact solution?
So this is also related to what we talked about maybe in the review session. How do you know how good your numerical solution is? So we said that keep increasing the order of the polynomials, for example. If your displacement function starts to converge towards something, towards an unknown function, then it's likely that you are getting closer and closer to the exact solution. If you diverge, let's say, you use 3 terms, you get a solution. You use 4 terms, you get a totally different solution. You use 5 terms, you get yet another totally different solution. That's a clear sign that that either you need to use a lot more terms or that your approximation is diverging. So, but that is not related to this particular fact. What I'm saying here is that given a particular matrix, that particular matrix represents a system of equations. How well you are able to solve those system of equations, that particular system of equations on a computer is what we are talking about. Okay. All right. So to get around this problem, what people devised was a good way to construct functions that are of the same class, meaning polynomials of increasing order, linear, quadratic, cubic, and so on, but very different from each other. And there's a lot of benefits to that. So the idea is that what we want are functions that don't look like each other, that are in some sense, quote unquote, orthogonal to each other. And what does that mean? You remember when we talked about vectors? Let's say I have three vectors, v1, v2, v3 in three-dimensional space. I can construct three vectors that are orthogonal to each other, right? E1, E2, E3, they are orthogonal to each other. If you have a tensor, then n1, n2, n3, the eigen directions, these are orthogonal to each other. So in the same way, what we want is to construct functions like h1, h2, h3, and h4, and so on, that are orthogonal to each other in some sense. What does that mean? We will use what is called an inner product. Just like in a vector, if you have vectors, we said two vectors are orthogonal to each other if the dot product is 0, correct? E1 dot with E2 is 0. So if that happens, then the two vectors are orthogonal to each other. Here, we are going to use this thing called inner product to determine if two functions hi and hj are orthogonal to each other. And how we define that is basically hix multiplied with hjx integrated over the domain 0 to L dx. And the fact that this inner product must be 0 when I is not equal to j, then we can say that hi and hj are orthogonal functions. Okay, and one example of that is, for example, sine of x, cosine of x in the interval 0 to pi. Can you tell me what would the integral of this be? Sine of x, cosine of x over 2 pi or over 0 to pi? Sine squared. Okay, so note that this guy is half of sine 2x, right? So, say that again. Yeah, it would be 0, and you can see that that would be equal to basically half of cosine 2x between 0 to pi, and I would have a -1 divided by 2 again, right? And of course, cosine of 2 pi is 1, cosine of 0 is 1. So 1 minus 1, this basically gives me 0. What this statement says is sine of x and cosine of x are orthogonal to each other on the interval 0 to pi. If I choose some other interval, they may not be 0, right? Okay, so this is an example of two orthogonal functions. And now the question is that since I have these polynomial bases, meaning 1, x, x squared, x cubed, and so on, this is an easy basis to construct. But if I want to construct an orthogonal set of functions using this set of functions, so this set of functions is definitely not orthogonal. You can check that very easily. But can I use this set of functions to construct orthogonal functions which are of the same polynomial order? And in order to do that, of course, the answer is yes to that. And in order to do that, we use something called Gramschmidt orthogonalization. And you can read the section in the book also for more details here. And I've written out the algebra also, how it is applied to functions. But what I'll do is I'll show you how it works for vectors first. And essentially, if you replace all the vector dot products with the function inner product that we just defined, you'll be able to do the exact same process for functions also. Okay, so here's the problem. What I'm saying is, let's say if I have three vectors v1, v2, v3 pointed in some arbitrary directions, they are not collinear, meaning they are not all pointing in the same direction, or no two vectors are pointing in the same direction. They are indeed three different vectors in three-dimensional space, but they are not orthogonal. Okay. What we want to do is to go from these three vectors to three independent orthogonal vectors. And the process that we will do, the process that we will use will be this Gramschmidt orthogonalization. And here's how it works. We'll say that the first function, the first orthogonal function, we'll choose right along v1. So if I have v1, v2, v3, I'll say that the first orthogonal v1 is equal to v1. And the second orthogonal v2, I'll construct using this v2, has to be perpendicular to v1. Can you tell me how you can do that? How can you construct a vector v2 perpendicular using from this v2 vector that is perpendicular to v1? You could use cross product. Is there an easier way?
Take the components of V2 in direction V1.
Right. So say, or basically, one of you, what you said was take the projection of v2 in the direction v1. Okay. So we'll do that. Let's write that basically first. So we will subtract from v2. We will subtract the projection of v2 along v1. What is the projection of v2 along v1? It's v2 dot with v1 perpendicular divided by v1 perpendicular norm. So hopefully you are able to see that this guy v2 dot with the unit vector along this direction, that would be the component of v2 along v1, right? So that's a scalar component. So I'll multiply that with a unit vector v1 divided by v1 perpendicular in the direction of v1. Now that entire thing is the component of v2 along v1. If I subtract that from v2, then what I get is v2 perpendicular, which is a vector that is perpendicular to v1. Okay. And if you keep repeating that logic for v3, go to v3, subtract out the component along v1 perpendicular and subtract out the component along v2 perpendicular. Those are these two components. You would get a v3 perpendicular. In three-dimensional space, that's the most you can do, right? You have three independent vectors, and you have constructed v1 perpendicular, v2 perpendicular, v3 perpendicular using these three vectors. The same process you can and you can check whether they are perpendicular to each other or not. I won't go through the details of that checking. The same logic essentially works for functions. If you have a set of n functions, for example, then you will take the first function to be equal to the first orthogonal function. Take the inner product of the following functions. So if you look at this, what we added here was the inner product of two vectors or scalar product of two vectors. You'll be doing the same thing for functions and subtracting the component of a function in the direction of another function, which is kind of a strange thing to say, what is the direction of a function? But since we have defined something called an inner product, that is basically very similar to the scalar product for regular vectors. So this is a process where you can use, if you have n functions, you can construct n orthogonal functions from that set. And there's an example in your book as it's mentioned here. And now look at these functions. The first one is still linear, second one quadratic, third is cubic, fourth is fourth order, and so on. And they look extremely different from each other. Okay, and there's a lot of good things that happen because of this. Let me ask you this. Not only is not only is the stiffness matrix very well conditioned, meaning that you can easily identify the solution and get pretty closely accurate, but there is yet another way to construct these orthogonal functions where you can make sure that the stiffness matrix. So if you remember not long back, but a little while ago, we constructed the stiffness matrix from these derivatives of those functions. Okay. Look at that particular entry. Kij is equal to C of Hi prime Hj prime. Okay. Now, what we have constructed are functions that are orthogonal to each other. Hi and Hj, their derivatives may not be orthogonal to each other. But if you were able to construct functions whose derivatives are orthogonal to each other, can you tell me what would happen? For what would be the structure of the stiffness matrix that you would get? Diagonal. How do you solve a diagonal matrix system of equations? It's basically n independent equations, right? So then you don't have to use a big computer to solve that. That's the sort of big benefit of using functions whose derivatives actually are orthogonal to each other, and you can construct those types of functions also. What we will do is we will adopt a similar idea to construct this one-dimensional finite element basis functions. Okay, so what we are solving again is that type of one-dimensional problem. Some body force, some traction at the end, some displacement specified at one end. We know the strong form, we know the PVW weak form, but I'll point out one thing here. Note that we are still going to keep this term. You remember in the PVW weak form, this was the term where we said virtual displacement is equal to 0. That works very nicely for the Ritz method and very nicely for when we were trying to derive these principle of virtual work method. But for finite elements, what we'll do is we'll keep this term around, and what we'll use is a slightly different way for enforcing that homogeneous essential boundary condition. Okay. So I'll show you what that means in a little bit. But keep in mind that since we are keeping this term in our virtual work functional, the problem statement would say that we have to find the real displacement that is in H1 and that satisfies the essential boundary condition. There's no change to that. And the other unknown is T0. So we still have to find T0 in this form of the problem statement, such that this G functional is 0 for all U bar in H1. There is no other additional homogeneous essential boundary condition in this form. So the virtual displacement in this particular form does not have to go to 0 where real displacement is specified. That logic was where we used that was logic that we used for the Ritz method. Here we are going to use a different implementation of that. So I'll tell you how we're going to do that. The approximation that we will use for real displacement and virtual displacement, note that there is no H0, or we are actually going to take, we are going to implement that H0 function slightly differently. So we will have in general these Hn functions, n approximation functions, and these n unknown coefficients for real displacement. Same thing for virtual displacement, where the coefficients have a bar on top, and it will indeed lead us to a very similar set of equations that the Ritz method gave us. So for example, for this particular bar, some body force, traction at the end, displacement specified at 0, I'm going to break this bar up into 4 parts as I'm showing you. If I do that, I create what are called these 5 nodes. Okay, these are 5 nodes and 4 elements. The length of each element is simply the total length divided by n, where n right now is 4 elements. Okay, and that would be simply, let's assume for simplicity that all of the elements are equal size. They don't have to be equal size. So the length of any element would be the coordinate of node I minus coordinate of node xi minus 1. So you could do 3 minus 2, 4 minus 3, or whatever. Okay. And the function that we are going to use to approximate displacement is this very special function that goes to 1 at one of the nodes goes to 0 at all the other nodes. Okay, this is and so this is h1 goes to 1 at node 1, 0 at all the other one. H2 goes to 1 at node 2 and 0 at all the other places. So similarly H3, H4 and H5. We have these 5 approximation functions with this very peculiar property that they go to 1 at their node and 0 at every other node. Note that they are indeed continuous. First question, are they in H1? If I take the derivative of this, any of these functions, and actually the derivative of any of these functions is given right here. Derivative of this first function, it's negative here, 0 everywhere else, so negative 1 over LE, 0 everywhere else. Positive here, 0 everywhere else, so that's positive here, negative in that region, 0 everywhere else. So this is the list of derivatives. Are these derivatives square integrable? Yes, we can square them and just integrate, find the area under that curve. So indeed they are in H1. So this is a valid class of functions, and you'll see very shortly what's the benefit of using these types of functions. Before I do that, let me actually write the functional form of these functions. So I'm going to write an expression for some hi that corresponds to, let's say, a function that goes to value 1 for node xi and goes to 0 for all other nodes. So in order to define such a function, I'll have to define it in this range where it's going positive, and in this range where it is going negative. Okay. Then in the first range, that is xi minus 1 to xi, can you tell me what would be the function? What would be a function that I would use as a function of x? It's a linear function, first of all, correct? So, and it has to go to 0 at x minus I, correct? Or xi minus 1. So how about this function? If I write something like x minus xi minus 1, is that a function that goes to 0 at xi minus 1? And is it linear? It is, right? Does it go to 1 at xi? So if I substitute x equal to xi, does it go to 1? Not necessarily, right? It would go to this value length of the element. So to make it go to 1, I will divide it by xi minus 1. This is a linear function. The denominator is some constant which is actually equal to the length of the element, and the numerator is a linear function that goes to 0 here. So it's a straight line that looks like this, only in this particular range. Similarly, the other function, can you tell me what that would be? Numerator would be xi plus 1 minus x. Yeah, okay. So if you say xi plus 1 minus x, that is fine. Or if you say the negative of that, that is also fine. That would be the numerator. The denominator would be xi plus 1 minus xi. So if we can check very easily. If I plug in xi here, if I plug in xi, which is this point, I know that the numerator and the denominator are the same. The value would be 1. If I plug in xi plus 1 here, the numerator is 0 and this function goes down to 0. And in this particular range, that also is clearly a linear function. So these two functions would define a general hi function. You just have to adjust the element over which you are defining these functions. And just because of the structure of these functions, they are also called hat functions. Okay. Can you tell me what would be the derivative of these two functions over the same ranges? Like for example, for hi, it would be positive in some region in half of its domain and negative in the other half of its domain. How would I take the derivative of this with respect to x? right? 1 over xi minus xi minus 1. What is this xi minus xi minus 1? Length of the element. So it would be equal to 1 over length of the element in the first half and negative 1 over length of the element in the other half. Right? Question? Okay. So that's basically the approximation functions that we are choosing. These are the derivatives. And what this will allow us to do is to approximate a real displacement that would look like this curve at the bottom. That if I have like a quadratic or a cubic exact displacement for real displacement, we will obviously not capture that quadratic or cubic because the highest order polynomial that I have in my approximation functions is linear. But what I am doing is I'm chopping up my length of the bar into multiple elements. So I would be able to approximate whatever the real displacement is as a piecewise linear polynomial. Okay, this is piecewise linear polynomial. And of course, the stresses would look like this. Note that the stresses jump between element to element. If I take the derivative of this, they do not match at the boundary, which is, of course, very important to understand when you get a finite element solution, that the derivatives will be jumping, that is, stresses would be jumping from element to element. It doesn't mean that the actual stresses in the beam or the bar are jumping. It's just an approximate numerical solution that we need to interpret correctly. We now know why stresses jump from element to element. It's because we chose approximation function in that manner. Okay. All right. So that's the approximation space that I'm using. What I'll do next is basically follow all the steps of the Ritz method. We know that if I substitute that approximation in my weak form, that's the original weak form that I had, substitute that approximation and follow through the algebra, I will get some system of equations exactly like the Ritz method, where we get the virtual coefficients out. In the bracket, we get k, a minus f, which is what we want to solve. And we want to solve it in such a way so that this g, which is the product of these two, goes to 0 for all arbitrary a bar, which will happen if we solve this system of equations. Let's look at the expression for the stiffness matrix K here. Exactly the same as we had for our Ritz method. If we were to write it out in terms of the actual functions that we chose, this would look like integral 0 to L C, and this vector H prime. Can you tell me what that would look like? Would it be a vertical or a horizontal? Let's say for this particular problem, I had these 5 functions. I have these corresponding 5 derivatives. What would that H prime vector look like? It would be a vertical vector, H1 prime of x, H2 prime of x, so on, and in general up to Hn prime of x. And similarly, the H prime transpose would then be a horizontal vector, H1 prime of x, H2 prime of x, so on up to Hn prime of x dx. Okay. Let me ask you now, let's say first let's consider all the, this will lead to a big matrix which would be basically the stiffness matrix, right? Let me ask you, what would be the diagonal terms, how would I obtain the diagonal terms of this matrix? H1 prime times H1 prime, that would go here. Let me say that gives me some value K11. Okay. Similarly, H2 prime times H2 prime, that would give me K22 and so on. So if I do that, I will get all the way up to KNN. Okay. Let me now take the first off diagonal. The first off diagonal is K12. Can you tell me what K12, how would I obtain K12? It would be H1 prime times H2 prime. If I go back to my basis functions, H1 prime is this, H2 prime is this. So this part of H2 prime will not contribute because the corresponding H1 prime is 0, but this part will, right? So that will give me some non-zero number, similarly K23 and so on up to Kn minus 1n. Let me ask you the next one, K13. K13 would be H1 prime times H3 prime. So if I go here, H1 prime times H3 prime, can you tell me what that is? 0. Similarly, H1 prime times H4 prime, H1 prime times H5 prime, they're all 0. That's the big benefit of this finite element basis. So all of these numbers that are away from the first diagonal, they're all 0. And the fact that we have H times H transpose means that this stiffness matrix will be symmetric. So all that you have to calculate are these n plus n minus 1 numbers to find the stiffness matrix for a finite element basis in one dimension. Okay. So in this particular one-dimensional problem, it so happened that the stiffness matrix turned out to be the main diagonal and the first off diagonal, top and bottom. But if you go to 2 dimensions and 3 dimensions, it won't just be these 3 diagonals. It would still be very diagonally dominant matrix, but in general, it won't be this simple. But the structure that there are a lot of zeros, meaning that this matrix is very sparse, will still be retained if you go to higher dimensional problems like 2D or 3D. All right, so this is basically what the stiffness matrix looks like. And let me actually now calculate what those diagonal terms would be. So KII would be C of HI, HJ, or HI, HI prime. We said that, so for example, if I go back here, H2 prime, okay, I would have to take this part and this part. So what I would do is I would split up this integral from 0 to L into only x minus 1 to xi plus 1, because that's the range where this hi is non-zero. Everywhere else it is 0, correct? And this particular integral, I will break it up into 2 parts, where it is going from xi minus 1 to xi, and the other one is going from xi to xi plus 1. In the first half, my derivative is 1 over LE and 1 over LE dx. And in the second half, my derivative is minus 1 over LE minus 1 over LE dx. So clearly, this is the integrand is a constant. It can come out. It is 1 over LE square times, if I do integral of xi to xi plus 1 dx, what do I get? Length of element. So what I get is 2c, and actually I'm missing a c, so let me write that c outside this integral, assuming that c is constant within the element, and I get 2c LE over LE squared, out of which I'm going to cancel one of this LE's in the numerator, so I get 2c over LE. That's all of those diagonal terms. So KII, any one of those diagonal terms is this 2c over LE. Okay, and only for the first and the last node. If you go here, the first node doesn't have both of these legs, right? One positive, one negative. And the last one doesn't have the negative leg. So for those two functions, KII, which is K11 or KNN, they will be equal to C over LE, not 2C over LE. Make sense? what would the off-diagonal terms be? We know that if the difference between the nodes is more than 2, or more than 1 actually, then it is 0. But if it is equal to 1, that's the one that will lead me to the off-diagonal terms. So that off-diagonal term would be basically 1 over LE times minus 1 over LE and C sitting outside the integral. And what that gives me is minus C over LE. Okay. If I use all of that and try to fill out the stiffness matrix that I would get, I'm pulling out C over LE out common. That means that I would have C over LE out common 2 at all of those diagonals, except the first and the last diagonal will be 1. So that would be 1, 2, 2, 2, 1 for this particular 5-node system, 5-node 4-element system, right? That's the main diagonal. All the off diagonals are minus C over LE. So C over LE goes out. What I'm left with is minus 1, 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 minus 1. Everything else is 0. Okay. That's my stiffness matrix for a finite element, one-dimensional problem with 5 nodes and 4 elements. Can you guess what would happen if I had 11 nodes and 10 elements? Same thing, length of element would be different for the same bar. If I chop it up into 10 elements rather than 4 elements, length of element would be much smaller. Inside here, it would be exactly the same thing. It would be 1, 2, 2, 2, 2, 2, all the way up to 10, and 1 at the 11th node, minus 1 on both the off diagonals, and 0 everywhere else. Right? So that's another reason why finite element types of approximations are very useful. Very quickly, let me tell you what the force vector looks like, and then we'll be done. The force vector given this is given by this expression. Note that we are still carrying around that unknown T0. First thing is, can you tell me what is the value of H1L? H1 function at L. Right, it's 0. H2 function at L, 0. The only non-zero function at L is H5. And that the value there is 1. Similarly, H1 at 0 is the only non-zero function whose value is 1. All the other functions, their value is 0 at H equal to 0. So if I use that, then I get H1 is 0, H2 is 0, H3 is 0, H4 is 0, and H5 is equal to 1. Similarly, H1 0 is equal to 1, but H2 is 0, H3 is 0, H4 is 0, H5 is 0. And that leaves me this integral. And assuming that the body force is constant, I can pull it out of the integral, which is basically what I'm doing here, body force out of the integral. And what I'd be integrating is h over dx, or h dx over the length of the element, which is basically the area under the curve of that element. So can you tell me what would be the area under the curve? Half of base times height, which gives me that half times base is 2LE times height is 1, which gives me that the integral is just LE. Okay, and you can actually verify that just by doing the same thing, by actually doing that integral, plugging in those expressions, and you would get that you get LE over 2 for the first one, and the last one, and the middle ones are LE. You add all of that up, you get the right hand side vector. And finally, you have that stiffness matrix, unknown coefficients that we wanted to find, and the right hand side vector. Okay. So maybe I'll just take one more minute and finish this off. You remember I said that I'll use the essential boundary condition and the homogeneous essential boundary condition slightly differently. Here's what we are going to do. The coefficient corresponding to H1, which was due to which was where the displacement is specified, I'm going to say that that is equal to 0. This is only so that I can enforce the homogeneous essential boundary condition. As soon as I say that, the first row of that matrix equation goes away. Maybe I should not cross out the unknown vector, only this part and this part. So keep in mind that T0 and all of these coefficients were unknowns that we were wanting to solve. So that T0 unknown goes away because I chose this A1 bar to be 0 because of the HEBC, which is exactly what happened in our Ritz method, right? All of the other things, this A1 function, can you tell me what is the A1 coefficient? The coefficient A1 is the coefficient of H1 function. That's the coefficient at the specified end. If the displacement there is specified to be, say, 1 inch, A1 is 1 inch. It is actually that degree of freedom. Unlike our Ritz method where there were some unknown arbitrary coefficients, these A1, A2, A3, A4 are actual values of displacements at their nodes. These are what basically degrees of freedom are, right? So, so this is known, and all of these forces are known to me, so they are specified. So now I can reduce that system down to this 4x4 where I have all my unknown degrees of freedom right here. The right hand side vector is all knowns. A1, that A1 is the specified displacement. Now I can just plug it into MATLAB. The MATLAB code is given to you on the next page, and what you get is this solution. For a constant body force, some traction at the end, the exact solution is quadratic. Can you tell me how many elements do I need to use to get a quadratic solution with a linear approximation? It doesn't matter how many elements I use. If I actually use infinite elements, I'll converge to that quadratic solution. But with a finite number of elements, I can never get there. And you can see that this blue solution that I have here is piecewise linear. Further, if you look at the axial stresses, stresses are linear. Displacement is quadratic, so stresses are linear. And the fact that the displacements from the finite element solution are piecewise linear means that the stresses from the finite element solution are piecewise constant. And you clearly see that the stress jumps between elements. And this does not mean that this solution is unphysical or wrong. It is this way because of the approximation that we chose. Okay. All right. So let me stop here, and then we'll continue on Wednesday. By the way, for the final exam, this is all that you need to know. Whatever we can cover on Wednesday and Friday is not on the final exam. Okay. All right. So see you on Wednesday.